Welcome to my channel. In this video, I'm going to walk you through the question 20 of our revision exercise. The question is about magnetic dipole. So we have a very small circular loop of constant current suspended at the height of h above the ground plane. The ground is expected to be perfectly reflective. The magnetic dipole as formed by the current loop is parallel to the xy plane. So he didn't say anything about the direction of the magnetic dipole. The axis is the vertical axis perpendicular to the ground. And you are asked to find the total far field radiated by the current loop. The formula for the magnetic dipole is given here. So let's start. So to begin with, let me try to understand what the question is. So what it says is you have a three-dimensional plane. And the dipole has a current. The magnetic current is parallel to the xy plane. So this is xy plane. Xy plane is parallel. This means the loop must be in this orientation. The radius here is a. So with a current loop here, you will produce a magnetic field pointing in either left and right. So let's assume that the magnetic dipole is parallel with the y-axis. So this means like this. So as you know it, this dipole will produce a electromagnetic field, so-called far field. And suppose you have an observation point here. The dipole itself has a distance. The current loop or the dipole has a distance, right? Say R1. The ground plane is supposed to be perfectly reflective. As a result of this reflective ground plane, we will produce an image. For magnetic current, the image magnetic current should be in the same direction as the original. So this is the current loop 2 is because of the refraction of this xy ground plane. So let's say this is loop 1 and this is loop 2, or magnetic dipole 1, magnetic dipole 2. Now we are going to find the let's write down the formula for the magnetic dipole first. The formula for the magnetic dipole is E J K I M I of m, L. L is the length of the dipole. And 4 pi r, and then r, and then sine. Let's say this angle is c. So this is the angle c. This angle is not in the same plane as theta, so bear in mind. And sine of c is equal to 1 minus sine theta. And now we are now dealing with a dipole parallel to the y-axis. So in this case, we have sine theta here. So this is the formula. Yeah, we have already derived it in the solution to question 21. Yeah, if you have question, right, you can either leave the question in the comment sections of this video, or take a look on the video for question 21. Okay, so this is the electric field, and the electric field for a horizontal dipole parallel with the y-axis is going to be JKIM L 4 pi r, and then 1 minus sine theta sine, and then okay, I hope this is clear enough. So the next thing that we are going to do is to find the combined electromagnetic field as observed by the observer. So if the distance between the dipole here and the observer is r of 1, we expect the distance from the origin to the observer is r, and we can draw a perpendicular projection. And for the image antenna behind the XY ground plane, we expect the distance between the image antenna and the observer to be R2. Okay, so empirically we have also derived the expression for R1. If you don't understand the division, you can just use the height here to work out the phase difference, the actual difference. So R1 is larger than R of 1. Sorry, R is larger than R of 1. By how much? By this amount. So let's say the height here is h. This here will be h, and then the theta here, and so this one is cosine theta. And similarly, for far field, all the angle formed by the vertical axis and the arrow pathway is beta. So we know R1 is equal to R, yeah, by how much, right? r minus h cosine theta. And for r2 is longer than r1 by how much? By this amount. So if we work it out, and then so this is the distance. So r2 is equal to r plus h cosine theta. And these two equations are intended for phase approximation. And for magnitude, we expect R1 is more or less equal to R2 or more or less equal to R. Or if the observation is very, very far away from the source, then this assumption is going to be valid for the magnitude, but not for the phase. For the phase, we have to use these two equations to work it out. Now, so what is the electric field as observed by the observer? The electric field as observed by the observer is going to be the combined electric field from antenna 1 and the electric field from antenna 2. And we are going to use this equation to work this out. Or this one, yeah? This one is more complete. And this one, J, K, I, M, L, 4 pi R1. And then this sine of Cassie. And then E, J, K, R1 and plus another R2 1 minus and then R2. So this is the combined electric field from the far as detected by the far destination at the very far end. And I have already highlighted the fact that for magnitude we can use this approximation. So this is the magnitude. So we do this fact first. K-I-M L 4 pi and R1 is assumed to be R. And both expression have the same expression for sine Cassie. And this one here will be different. This will be dealt with using the phase approximation. So this is what we are going to get. Now the next thing that we are going to do is to work this out. What we can do now is to substitute R of 1 into here and R of 2 into here. Okay? So the next thing, so E is equal to E of 1 plus E of 2. And it's going to be K I of M L 4 pi R, and then this big chunks of expression and then E of jk out of 1, which is equal to and then rho plus cosine beta. Now we can extract the common terms here. The common terms is k of r. So what are so this is what we are going to get. Now this expression is looks very familiar. Yeah, we can use cosine to rewrite it. Yeah, cosine kh beta, and remember there is 2 here. So I miss out this expression, right? I should 1 minus sine beta square sine. So this bit here is the array vector, and this one is the element vector. For this scenario, we expect both the array vector and the element vector will contribute to the far field, to the shape of the beam. So basically, this is the answer to the solution to the question. If you want to find the magnetic field, we can just use H. Let me see. Minus H and then E. So this is what you are going to get. Let's make sure the direction is correct. This guy is this one, and this guy is this. Yeah, so everything should be correct. So the next thing is just to divide this by that much, right? I don't think you will get any mistake. So this is what you expect to get, right? The electric field and the magnetic field is given, and if you want to find the normalized value, and this is the normalized value. This is the normalized value, and you can use this to work out the nodes, the directivity, on the half power beamwidth for theta. For theta, I don't think you can. Yeah, maybe you can get the value for phi as well. Okay. If you have any questions, please leave your question to the comment section of this video. Other than that, I think this is the end of the video, and I also want to remind you this expression here would allow you to work out all the nodes, directivity, and half power beamwidth. As a result, I might have one more supplemental questions for you guys. Let's see what's going on. And the supplemental question will be about the electric Bible with the reflective ground band, and you may be asked to work out all the nodes, whatever. I think it's quite handleable now. Thank you.